Hello everyone. This is the video where I tell you about DynamoDB Accelerator, which is also known as DAX. And I gotta tell you, I'm really super excited about this video because I've used DAX quite a bit in the past, so I'm quite familiar with some of the low-level details that I'm very excited to share with you today. So this video is going to consist of an overview of what DAX is, a small talk about what use cases DAX is suitable for, followed by an overview of how it works, then a deep dive on how it works, and finally some talk about best practices. But before I get into that, I just briefly want to mention a neat tool I came across when working with DynamoDB, and the tool is called DynoBase. DynoBase is an application that's devoted to making your life easier when working with DynamoDB. It includes features that allow you to perform some normally tedious Dynamo tasks, as well as visualize your data in a pretty intuitive way. And DynoBase has a 7-day free trial, so I recommend you try it out to see if it's right for you. You can find a link in the description section below. So now getting into the meat of the video, I really want to just jump right into DAX, but before we do that, I think we need to set the stage and quickly talk about what caching is at its most basic level. So first, let's talk about what is a cache, why is it useful? So a cache is, in its most basic form, it's just a data storage layer that contains a subset of your data. So imagine you have a country database where you have country IDs and then some details about those country objects. Typically, when we try to retrieve data from a database, there's a round trip cost of making that connection to the database, making the query, and finally getting those results back. Caching is an optimization technique that allows for duplication of this data, and that duplicated data sits in memory typically on a local machine, and instead of reading that data from the database itself, your application will have business logic to first attempt to read it from your in-memory cache before you go and get it from the database. So it essentially serves as a mechanism to save a trip to the database and deliver some quicker performance for your get operations. So like I mentioned, a cache entry is usually stored in memory to quickly retrieve and serve content. And caches can be local or remote. You can have just a local cache that's serving memory directly out of that machine. You can have a remote cache, which is something more similar to how DAX works, where you have multiple nodes that are working as a unit to act as a cache. And we're going to get more into those details later. So before we jump into DAX specifically, let's just go over again how this works. So say for instance, you have a Node.js app and that's hosted on an EC2 machine in AWS, and you have requests that are coming in for a country ID, for instance. What your application would do is first check your cache for the country ID that's being queried on. If the item is in the cache, it would serve it right back right away. If the item was not in the cache, then you would go to the database, retrieve that data there, and before you return the row back to the caller, you put that row in the cache so that next time when a retrieval operation comes in, that row will be in the cache, so you don't have to make another trip to the database to get the record again. Finally, to return that value back to your client. So this was a brief overview about how caches work, but the next logical question is, how does DAX fit into this whole picture? We know that DAX is for optimization. We know DynamoDB is a database. What does DAX do and how does it make my life easier? I'm sure you're all asking this question now. So what is DAX? So DAX is a fully managed, highly available caching layer for DynamoDB. It delivers microsecond level performance, and if you've worked with Dynamo in the past, you know that the typical level of performance that you get on a get item operation is something in the realm of 5 to 8 milliseconds, I would say on the lower end. And if you're doing something a little bit more bulky with query operations that are retrieving multiple rows, then maybe like a couple hundred milliseconds, maybe 50 milliseconds if you're lucky. But that's the kind of performance that you're going to get out of normal DynamoDB. DAX takes that to the next level and delivers microsecond level performance for you. So you definitely get a boost in the performance department at the cost of some limitations of DAX. And that's what I want to kind of talk about in the next few slides here. So DAX is horizontally and vertically scalable. And like I mentioned, DAX consists of nodes, and each node is an EC2 machine, and a DAX cluster works together with these nodes that are in the cluster to serve some highly available content that's duplicated across all of your nodes. So DAX is horizontally scalable in the sense that you can easily add more nodes to your cluster. And it's vertically scalable in the sense that you can throw more CPU or more memory or faster performing memory also at your nodes to improve performance in the vertical dimension. Just keep in mind, one node will always serve as your master, which is the ledger for writes, and the other nodes that are in your cluster will serve as your read replicas. And we'll get more into that in the next few slides as well. So DAX by default supports get, query, and scan operations on the data retrieval side, and update, delete, and put operations on the data modification side. It also supports caching for LSI, GSI operations, and any range key operations that you're doing when performing queries. It allows for easy migration from just your standard vanilla DynamoDB to DAX. Typically, you just have to switch out your SDK that you're using, and then you just switch the endpoint to point to the DAX cluster as opposed to the Dynamo table. And finally, like I was mentioning before, your cache is hosted on multiple nodes in a cluster, which are actually just memory optimized EC2 instances, and the cost model is that you just pay per node. There's no additional costs that are incurred as a result of using DAX. You just pay for the hardware. So now I want to move on to what applications is DAX suitable for, because like I mentioned, it gives you all these performance boosts. It does all these great things for you, makes things really fast, so you can do all this optimization in your application. But unfortunately, all this performance boost does come at a cost, and the limitations that arise out of using DAX sometimes make it such that certain applications aren't suitable candidates. So let's talk a little bit about that. So when should you use it? When should you not use it? So you should use it if you have an access pattern such that you have consistent or burst-like traffic on the same set of keys. Ideally, those keys don't change very often, so you have limited write patterns on those keys. Also, obviously, I've kind of mentioned a lot about performance here, so if you do require that microsecond level response times, then you should definitely look into using DAX. I'm going to get more into the limitations next. Thirdly, if your use case can tolerate eventual consistency. So what eventual consistency means in pretty basic terms is that you're going to have scenarios or cases when you have data that exist for a specific key on your DynamoDB table that is inconsistent with what exists on your cache. So say for instance, you have a DynamoDB table where your ID is ABC and the value is 1. In your Dynamo table, that's the row as it exists, ABC with value 1. It's possible, due to the way that DAX works, that if that row gets modified, the modification may not propagate into the DAX cluster, so that when a query takes place on the DAX cluster, it will potentially be serving up stale content. So this is one of the limitations that you have to factor in when you're deciding whether or not you want to use it, because this can cause some very, very difficult to debug scenarios. And if you're not aware of it from the get-go, it'll cause some very complex bugs in your application. And finally, you should use it when your application is read intensive and not write intensive. Like I kind of alluded to before, you have one master with multiple read replicas. If you have a very read intensive application, your master node will very quickly become overburdened with traffic, and write intensive applications just don't really make sense for caches. Caches are typically used for applications with a lot of reads and accesses on your data with not a lot of writes. So far we've talked about what caches are, what DAX is, a little bit about how it works, and kind of if your use case is suitable for it. Now I kind of want to jump into a little bit of an overview to start about how DAX works under the hood, followed by a more comprehensive deep dive, and that'll kind of really show you some of the low-level details about why eventual consistency can be problematic for applications. So let's move on now into how it works from an overview. So say you have a transactions table, and this Dynamo table stores credit card transactions in this case. And say you decide to set up a DAX cluster that's going to sit in front of your Dynamo table because for whatever reason you have a very high read pattern on this table, and your read capacity usage is starting to get expensive, right? You don't want to be paying 10,000 read capacity units on your transactions table. You're looking for something that's going to be cheaper and also give you a performance boost. So you say, okay, let's use a DAX cluster. So you set up your DAX cluster in the console, and say we specify 3 nodes in our DAX cluster. By default, DAX will assign one to be the master and the other 2 nodes to be read replicas, which are going to contain copies of the master's cache. So behind the scenes, any writes that occur will automatically first go to the master and then propagate their data into the read replicas. So you have this very natural sharing of information that's going on between the nodes in your cluster. So DAX will also set up a load balancer with an endpoint so that whenever a request comes in, it's kind of a round robin approach into determining which node is going to actually serve the request. Could be your master, could be one of the other 2 read replicas. So say for instance, if a request comes in to your cache and say it's a read operation, so you're trying to find maybe transaction ID T1, let's just write that down, you're looking for T1 in your transactions table. How's that going to work? So you query T1 against the DAX endpoint. You're going to check the cache to see if T1 exists in the cache cluster. In the case that it does, you just return it back to the client right away. In the case that it doesn't, you need to go and retrieve that data from your transactions table. So to go and query your DynamoDB database, retrieve that data, insert it into your DAX cluster so that it's available for our next query that comes in before finally returning it back to your client. So that's how it works from the read perspective. We had 2 operations. We had what we call a cache miss when we found out that the entry didn't exist in the cache, and then we had to go and retrieve it from the source of truth before we populated it. So that was the read flow. So how does it work for the write flow? So for the write flow, if there's a write to your DynamoDB table, that write will be transactional in nature. Your first write will occur on the Dynamo table itself. The second step to be performed is to write that same row into your cache so you get that data primed in your cache, because in all likelihood, if you're writing an item to your table, it's very likely that you're going to read that item from that table shortly thereafter. So that's the write flow of how data gets into the cache when data is modified in the source of truth. So that was a quick overview from a high-level perspective. Now let's talk about the low-level implementation of DAX and how it works from the most basic levels. So how it works from the advanced perspective. So again, we have our transactions table. And say we decide to set up our cluster again, and this is kind of a zoomed in view of a DAX cluster. Say we're just looking at a particular node, say it's our master node in this case, just to make our lives a little bit simpler. So behind the scene, DAX will maintain 2 sets of internal caches that are shared across your DAX cluster. So the first one is called an item cache, and the item cache's responsibility is to store mappings of keys to values. So your keys being the ID of the item and the value being the item itself. So if you had T1, that's the key in this example, and the contents of that row, say it's a purchase transaction and it's a $50 value and it took place on a certain date, all that metadata is the value. So we have a mapping between the key, which was T1, and the value, or the object, which is a transaction in this case. So the intention of this cache is to maintain this mapping whenever updates occur on your Dynamo table. So say for instance, if a request comes in, it's a get item API and it's pointed to your DAX cluster. Say we're using C1 here, that's our partition key, and our range key is date. We will first, like I mentioned before, attempt to see if it's in the item cache. If it's in the cache, we return right away. If it's not, we go and look up that item in the Dynamo table before we finally store it in our item cache with the C1 and date hashed as the key and the actual value stored alongside that hash key. So that's the item cache's responsibility. So anytime any get item operations occur, they're going to always look at the item cache, and anytime any modifications occur to the items on your table, they're going to be transactionally updated into your item cache. So the next time a lookup occurs, that value will be sitting in your item cache. So the second cache that occurs is what's called the query cache. And the query cache is what drives, as you would expect, your query operations. But it works in a similar but also a very different way. So the query cache consists of a mapping between an ID and a list of objects, because as we know, when we submit a query, we submit a key that we're interested in and also a criteria. In the range key case, maybe it's your range key is date and you only want things that are within the last 7 days. So how the query cache works is slightly different. So when a request comes in with this combination, say C1 plus a date criteria, the same flow of operations will happen. We'll first look into the cache, see if we have this combination of criteria ever queried for before. If we don't, then we'll go and retrieve that data. And finally, we'll store that data inside the cache for later use. So if someone calls again within the next 5 minutes or so, then we'll just retrieve from the cache A, B, and C and serve up that data very, very quickly. So obviously with this implementation, you get very exceptional performance. You don't have to actually perform a query on your Dynamo table. Instead, you're just looking in a cache and it's an O-to-the-one lookup. So you get that data back right away. But I'd encourage you to do a thought exercise here about why this is a problem. And maybe you want to pause it to think about it a little bit, because these rows, right, they're replicated. A, B, and C, they're replicated in the query cache. The A is also replicated in the item cache. And then we have a transactions database, which is the authority on this data. So I want you to pause for a second, and if you can, try to think of a scenario when you update items in this table, problems with what data you serve back. So maybe you want to take a pause, take a minute or so to think about that right now. So hopefully you thought about this problem, and let's walk through why this setup is an issue and why you should probably never be using query caches. So think about this case, right? The setup that I've already described to you. We had a previous lookup where we did C1 and date and we retrieved item A, okay? We've already recognized the fact that if a update occurs on the Dynamo table, there is a delay between when that update is in the Dynamo table and when that update is reflected in the item cache, right? So that's problem number one. There's an inherent delay between these two tables. That problem is enhanced in the query cache scenario, because what query caches do is they cache a criteria and a list of results. So if any of these results, if A, B, or C changes while this row exists in your query cache, then the next time a query comes in for C1 plus this specific criteria, this data may have already changed on the DynamoDB table and you will never know it. So this is part of the reason that caches on the query side are very, very ill-advised. You have the very high likelihood to serve up stale data. So be very, very careful about working with caches when you're using queries. So this was a more in-depth look about how it works behind the scenes. Now I kind of want to go into best practices, things you should know about when you're using DAX, or maybe you're thinking about using it in your next project. So the first one is directly tied to my previous point, and that's to don't cache queries unless you understand the implications. So understand that you may have inconsistent data. If you're using your Dynamo table as a source of truth, that is for some very mission critical information, maybe it's like credit card transactions, then you don't want to be using query caches. You may not even want to use caches in general, since by definition they introduce eventual consistency. The second one is from the monitoring perspective, and it's to monitor and scale your nodes accordingly based on workload. As you know, you're using EC2 machines, you're paying for that always on functionality. I don't think there's auto scaling for DAX yet, but if there is, that'll be a great new feature. But as a result, you really need to monitor your usage pattern. I would suggest starting with the lowest level type of hardware, see if that fits your use case, and then maybe you can add more nodes to serve as read replicas or beef up your replicas to be more intensive so they can serve more traffic. And the third point is to beware of single point of failures if you decide to share your cluster across multiple tables. This is a kind of a neat feature. You can share your cluster across multiple DynamoDB tables, so you can store all amounts of data in there and they can be totally unrelated. The problem with this is that if you're sharing this across different services or different use cases, it's possible that a read or write access pattern to one table can cause a cascading failure in your cache that can all of a sudden start impacting your other application that happens to also use the cache, but a different section of the cache. However, if it starts failing, it doesn't matter. Failure is failure. There's no sections of failure. There's no partitioning of failure. It's either up or down, right? So in this case, you can have certain parts of your application impacting other parts of your application. So just be aware of doing this if you decide to take this kind of shortcut. And the final one, which has to do with eventual consistency, is when in doubt, use your DynamoDB record as the source of truth. Don't perform operations where you read from the DAX cluster. Use it as a source of truth and then write to your Dynamo table. So like we said, there's eventual consistency. So the likelihood of that data being out of date at some point is not, I don't want to say high, but it's possible. So keep that in mind when you're designing your application. Be fault tolerant, but also try to deliver the best experience possible for your customers. So hopefully you like this video. I have many more on DynamoDB, including this one on the right here about DynamoDB schema design. Also, please don't forget to like and subscribe so that you don't miss out on next week's video. Thanks so much, folks, and I'll see you next time.